Good afternoon. Today, Sammy, Haley, Leah, and I will be presenting on simple linear regression. Please see our icebreaker. I'll allow you a minute to read and analyze the image. I hope that did put a smile on your faces. Our objectives today are to identify the purpose of simple linear regression and its application to quantitative research, and 2, to demonstrate the application of regression in nursing research. There are many different types of regression as seen in this table. For the purposes of this presentation, we will review simple linear and multiple linear regression. Simple linear regression has one dependent continuous variable and one continuous independent variable with a relationship that's linear, whereas multiple linear regression has one continuous dependent variable and 2 or more independent variables that may be continuous or categorical, and it also shows a linear relationship between both. Please feel free to review the other types when you're able to do so. So what is a simple linear regression? It is a linear model in which one variable or outcome is predicted from a single predictor variable. The equation can be seen here. So it's the outcome equal model plus error. Last week we covered correlation, which is calculated with values that have already been measured. Linear regression differs in that you can use the strength of the correlation between 2 known groups of information to predict an unknown value of one variable. If we have calculated a consistent relationship between the variables, the stronger the correlation, the better our ability to predict the values. We will talk more about this later in our presentation. So as you know, y is the outcome or dependent variable, and x is the predictor or independent variable, where b1 is the regression coefficient associated with the predictor, and the regression intercept, or b0, is the value of the outcome when the predictor is 0. Epsilon is the error of the estimate. The b-value tells us the slope of the regression line. It's a flat linear model or horizontal line which occurs when b is 0. A straight line is defined by the slope b1 and the intercept b0, the point where the line crosses the graph's vertical axis. A b-value different from 0 indicates the direction and strength of the relationship between the predictor and outcome variables.
Thank you, Jody. So as we learned previously, when we square the differences between the observed and expected values, we can calculate the total error. We can apply this to the linear model. So to assess the error, we use a sum of squared errors, and in this case, they're called residuals, and we get the residual sum of squares. So the model is never going to be a perfect fit for the data, and it can overestimate or underestimate the observed value, and the residual is that difference. So the sum of squares, residual sum of squares is, if the residual sum of squares is large, this indicates a lot of error in prediction. And if the square differences are small, then this indicates that the line is representative of the data. There is also the total sum of squares. The total sum of squares is the total squared deviance between each observed value and the overall mean, and it represents how good the mean is as a model of outcome values. Lastly is the model sum of squares. If the model sum of squares is large, this tells us that the linear model has improved prediction of the outcome variable compared to using the mean. If the model sum of squares is small, this tells us that the linear model is not much better than the mean at predicting the outcome variable. So this is a visual depiction of the total sum of squares on the top left, the residual sum of squares on the top right, and the model sum of squares on the bottom. Give you a second to look at that. So the sum of squares is useful because you can calculate the improvement due to the model compared to the mean. So the R squared is the coefficient of determination. R squared tells us the proportion of variance in the outcome variable that is predictable from the model and can be expressed as a percentage. And you can see on the little clipboard image there the formula to calculate that. Accuracy of predictions. So Pearson's correlation coefficient can be obtained by taking the square root of that R squared, which is the coefficient of determination. Recall that Pearson's correlation coefficient of R can take a value between -1 and +1 indicating a strong positive relationship, 0 indicating no relationship, and -1 indicating a strong negative relationship. A larger correlation indicates that the prediction will be more accurate. For example, if we have a correlation of 0.8, the linear regression model would only account for 64% of the data variability. If we have a correlation of 0.3, however, the linear regression model only accounts for 9% of that variability. This correlation coefficient gives us an idea of the overall fit of the model, which is the correspondence between predicted and actual outcomes of the value, while R squared gives us an idea of the proportional size of the fit.
Okay, so next we have the F statistic. It's used for simple or multiple regression to test the overall fit of the model. It's a measure of how much the model has improved the prediction of the outcome compared to the level of inaccuracy of the model. If you have a large F statistic greater than 1, this indicates a good model. This tells us that there's a large improvement in prediction of the outcome and a small difference between the observed data and the model. Note that the F statistic uses the mean squares, the sum of squares divided by degrees of freedom, rather than the sum of squares, as was used in our previous calculations. A p-value can also be obtained from the associated probability distribution of the F statistic, which tells us the probability of getting an F at least as big as the one we have if the null hypothesis were true. The significance of R squared can also be calculated from F. F tests the null hypothesis that R squared is 0, i.e. there's no improvement in the sum of squared error due to fitting the model. And we have the T statistic, which is used to test the null hypothesis that the B value is 0. If the test is significant, this indicates that the value of B is significantly different than 0, and the predictor variable significantly contributes to our ability to estimate the outcome values. With a T distribution, a p-value can also be calculated. So if the p is less than 0.05, it's assumed that the value of B is significantly different than 0, and the predictor variable significantly contributes to estimating the outcome. Similar to the F statistic, the T statistic is based on the ratio of explained versus unexplained error or variance. Here, we're not as interested in variance, but if our B is large compared to the error in the estimate. Outliers are also important as they're a source of bias in linear models. They can affect the estimates of regression coefficients. As you can see in the example, the outlier makes the regression line flatter, which makes B1 smaller and increases B0. It is therefore important to detect outliers. We can do this when we calculate residuals. Outliers would have large values because of the greater difference between the observed value, the outlier, and the predicted value. Sample size is also important. So due to the central limit theorem, larger sample sizes allow us to assume a normal sampling distribution for our B values. The most common rule is 10 to 15 cases for each predictor. However, the sample size depends on the strength of the relationship that we're measuring. We also have a number of linear model assumptions. So we've already learned about the assumptions of additivity and linearity, independent errors, homoscedasticity, and normally distributed errors. The assumptions that we haven't yet covered include predictors not correlated with external variables. So recall that external variables are variables not included in the model, but that affect the outcome variable. This assumption indicates that the external variables should not correlate with any variables in the regression model. The model becomes unreliable when external variables are correlated with the predictors. We also have variable types. So for simple regression, our variables are continuous, interval, or ratio. No perfect multicollinearity. If there's multiple predictors, so this doesn't necessarily apply to linear regression, because remember you only have one predictor variable, the relationship between two or more of the predictors should not be perfectly linear. So a correlation between the predictors should not be too high. And non-zero variance. There should be some variance in the predictors. There shouldn't be a variance of 0. Violation of these assumptions mainly influences significant tests and confidence intervals. If confidence intervals are inaccurate, we can't generalize our model to the population. If the assumptions are met, it increases the likelihood that a regression model from a sample is the same as the population model. Of course, there's always a possibility that it's not.
It's difficult finding an article that only uses simple linear regression. There is more merit and a better understanding of an outcome when more variables are explored and considered. The article we will be discussing today will have both simple linear and multiple linear regression. We will not go into detail about multiple linear regression, but will briefly explain the reasoning and importance of it. The study aimed to determine the relationship between the nurse's perception of ethical climates and job satisfaction. Job satisfaction can be related to poor job performance, lower productivity, high staff turnover rate, and decreased quality of care. Although this research study was completed in Ethiopia, nursing ethics and job satisfaction is applicable everywhere. This was a cross-sectional design producing and analyzing both descriptive and inferential statistics on SPSS. Pearson's correlation, simple and multiple linear regression analysis was completed. All analysis was conducted at a 0.05 significance level. Participants. All nurses who are working at the hospital that had work experience of at least 6 months were included in the study. A simple random sampling method was used. A total of 252 nurses participated. Data collection. A demographic, ethical climate, and job satisfaction questionnaire was distributed. The ethical climate questionnaire of Victor and Cullen was adapted. It consisted of 5 different climates: caring climate, instrumental climate, law and code climate, rules climate, and independence climate. Each item was measured on a Likert scale, 1 being completely false and 5 being completely true. A questionnaire adapted from the Minnesota Job Satisfaction Questionnaire was used. There were 24 items, each using a 5-point Likert scale, 1 being completely dissatisfied and 5 being completely satisfied. So was regression analysis appropriate for this study? Remember that regression is used to predict outcomes and estimating relationship between variables. The goal of the study was to determine if ethical climates, or predictor variables, had an impact on our job satisfaction or outcome. So yes, it was appropriate. Let's review a couple assumptions for linear regression to see if the study followed them. Normally distributed data. The study used the Kolmogorov-Smirnov and Shapiro-Wilk test and determined that the variables were normally distributed. Also, with the sample size, it follows the central limit theorem. Are the variables continuous? Yes. Although the Likert scale was used, the data became continuous when all the responses were summed together and a mean statistic was calculated. Are the relationship between variables linear? Yes. This was demonstrated with the Pearson's correlation test, where linearity is assumed. So what did this study show? When looking at linear regression, we want a line of best fit, a line that best summarizes the pattern of the data. One way to show this is calculating Pearson's correlation coefficient. A larger correlation is an indication that the prediction is more accurate. The results of the study showed that there was a moderate, positive, and significant correlation between the ethical climates and job satisfaction, with instrumental climate having a negative correlation. Finally, a simple linear regression analysis was completed for each ethical climate with job satisfaction as the dependent variable. As you can see, the results showed that the law and code climate, rural climate, caring climate, and independence climate significantly and positively affected nurses' job satisfaction, all with a p-value of less than 0.01. On the other hand, the results show that the instrumental climate significantly and negatively influenced job satisfaction. Like we mentioned before, this article completed simple and multiple linear regression. Similar to simple linear regression, the goal of multiple linear regression is to model the linear relationship between our independent variables and our dependent variable. As you can see, an equation was created with the multiple regression analysis to predict job satisfaction using ethical climates as predictors. We wanted to point out that after using multiple linear regression, it is interesting that while law and code, caring, and independence climates continue to have a significant effect on job satisfaction, rules and instrumental climates did not. Researchers also reported that the R-squared value of ethical climate was 0.601, demonstrating that ethical climates explain 60.1% of the variance in job satisfaction. The reported F statistic is also greater than 1 at 76.76, telling us to reject the null hypothesis because the independent variables in the model improve the fit of the line. When each individual variable was analyzed, it each had a significant influence on job satisfaction, but all variables were analyzed at the same time. It showed that some variables had less of an influence compared to others. Multiple regression is advantageous in that it can determine the amount of potential influence each independent variable may have on the outcome, leading to a more accurate and precise understanding of the association between the variables. Our article critique. There were a couple things we thought the article could have included that would have been more helpful for our understanding. For example, the researchers could consider including scatterplot graphs of the data to show that they can assume homogeneity of variance. This article is also a good example that being published doesn't mean that it is free of statistical errors. When the researchers reported that 60.1% of total variance was explained by ethical climates, they also concluded that 48.9% was explained by other factors. This should have been 38.9%. The researchers also chose to not report standardized regression coefficients. It would have been more helpful to explain why, as we had to assume that they chose not to because the measurement levels were the same for all the independent variables, and therefore they did not have to standardize the coefficients for direct comparison. This standardization will be discussed in further detail later in class. So how can regression be used in nursing? Regression is important in helping to predict outcome based on a relationship between variables. It is a movement from association or correlation to examine causation. However, it does not imply cause and effect. Regression, whether you choose simple, multiple, or logistics, can be used in examining different aspects of healthcare and nursing. Regression can be used in predicting variables that influence length of stay, readmission, moral distress, burnout, etc. Regression analysis can be a powerful tool for healthcare decision-making and in the improvement of patient care.
So the key takeaways. We want you guys to remember that simple linear regression is a parametric statistical method that allows us to predict the values of one variable from another using a straight line, the straight line representing a summary of the pattern of the data. Simple linear regression involves one predictor variable and one outcome variable. Linear regression is related to correlation, and a stronger correlation indicates that our prediction will be more accurate. So here are our references, and now we're going to play a Kahoot. Okay, hang on, I'm gonna figure out how to stop recording.